In the third session of machine learning, we will cover the linear regression. In this part 1, we will look at the ordinary least squares, OLS, the maximum likelihood estimates, MLE, and the R-squared. This video was produced in Korean and translated into English. My voice was generated using AI text-to-speech. Let's take a look at the full table of contents. Chapter 1 examines ordinary least squares, OLS. In Chapter 2, we will look at the total least square, TLS. And in Chapter 3, we'll look at the locally weighted regression, WLR. In Chapter 4, we will look at the random sample consensus, RANSAC. In this video, we will look at the least squares method for single and multiple features. We then look at how to estimate the regression line using the maximum likelihood estimates, MLE. We then look at how to evaluate the performance of the model. First, let's look at the least squares method for a single feature. Let's take the data below as an example. There are training data and test data samples. It has a single feature X and one target value Y. We want to predict the target values of the test data by learning the training data. Our goal is to find a straight line that best fits the training data. This is the regression line. Plot the training data in two-dimensional space and create a model for the regression line like this. The Y value of each data point can be expressed as the Y value of this regression line plus the error value. The size of the error is this much. If we make the regression line like this, the total error will be larger. Here X is the independent variable and Y is the dependent variable. Or they are also called predictor and response variable. And the W and B are the parameters of the model. W is the slope of the line and B is the intercept. To find the regression line, we need to determine the model parameters, the slope and the intercept. To determine the slope and intercept, we can use the least squares method. Let's look at some assumptions here. Epsilon, the error, follows IID normal distribution. The average of epsilon is 0. The variance of epsilon is sigma squared. These values are assumed to be constant. And since the epsilon is IID, the covariance is 0. The objective function for the least squares method is defined as follows. Determine the W and B that minimize the sum of squared errors. Since the epsilon is y minus y hat, we can write it like this. And y hat is wx plus b, so we can write it as follows. The sum of epsilon squared of the blue line will be greater than that of the red line. Among numerous lines, we need to find the one with the minimum value of that. We can use mathematical methods to find the solutions, W and B, of this objective function. We can find the solution by differentiating this with respect to W and B, respectively, and solving the simultaneous equations. However, this method cannot be used when there are many data points or many features. In that case, the solution can be found through numerical methods. For example, we can use methods like quadratic programming. Machine learning uses numerical methods because it deals with large amounts of data. This process of finding the optimal regression line is the training stage. In the prediction stage, To predict the target values for the test data, you can use the regression line fitted to the training data. Next, let's look at the data with multiple features. There are multiple features in the training and test data. Given two features, the data points can be plotted in 3D space as follows. There are two x-axes that are independent variables. In this case, we use a regression plane instead of a regression line. If there are many features x, it becomes a regression hyperplane. The equation of the plane can be expressed like this. If there are k features, then there are k parameters w. And then there is the intercept, b. In this case, the error is also measured as the difference between y hat, a point on the plane, and the actual y. The assumptions are the same as on the previous page. Once the regression plane is determined, we can predict the target values for the test data. If a test data point is located at this point, the predicted value will be this value. The objective function for the least squares method is the same as on the previous page, where w is a vector. By differentiating the objective function with respect to w and b, and solving the simultaneous equations, you can find the optimal solutions, w and b. Again, if you have a lot of features and a lot of data points, you won't be able to use this method. In that case, the optimal w vector and b can be obtained through numerical methods. This time, we will look at how to estimate a regression line using maximum likelihood estimates, MLE. Let's assume that we know that the data consists of values drawn from this linear model. Here, the epsilons are assumed to be independent, identically distributed, and normally distributed. Let's consider these training data points and the regression line. The error for this data point is this much. This data point is most likely to be found at the y-hat point, but it was actually found at this point. The PDF value f at this point is this much. The larger the error, the smaller the PDF value. For this data point, the error is small and the PDF value is slightly larger. Let's look at another regression line with large errors. The error for this data point is very large and the PDF value is very small. The regression line A with larger PDF values is better than the regression line B. You can find the W and B of the regression line that has the largest product of the PDF values, or probability values. This can be solved using MLE, the maximum likelihood estimates. And the result is the same as the result of the least squares method. Assuming that the error, epsilon, follows a normal distribution, the PDF value for this distribution can be written as follows. Y minus y hat is the error, epsilon. The product of the PDF values for all data points is defined as the likelihood function. Then we can find the W and B that maximize this function. However, this equation is mathematically inconvenient. So we use the log likelihood function, which takes the log of both sides. Taking the log of both sides and simplifying it gives us as follows. Then we just need to find W and B that maximize this. Here, the first term is independent of the W and B, so it can be omitted. Then you just need to maximize this part. This is how we use MLE to determine the W and B. If we remove the minus sign here, we can change the max sign to the min sign. This equation then becomes equivalent to the least squares method. In other words, maximizing the log likelihood is equivalent to minimizing the squared error. Therefore, MLE and least squares method give the same results. Next, let's look at how to evaluate the performance of a linear regression model. Performance can be measured by mean squared error, MSE, or R-squared. Split the dataset into training and validation data. Sample the dataset to create subsets for training and evaluation. In this example, we removed some data points from the dataset and used them as validation data. And we apply the regression line fitted to the training data to the validation data to evaluate the performance of the model. This is the regression line generated from the training data. This line is then applied directly to the validation data. Mean squared error is simply measured as the average of the squared errors. Another measure is R-squared. First, let's consider the total variance of y. This is total sum of squares. The overall average of y is this straight line. And the y minus y bar for this data point is this much. The y minus y bar for this data point is this much. SST is the sum of all these squared. And y minus y hat is equal to this much. This is the error, or residual. The sum of squared errors is called SSE. And y hat minus y bar is this much. This is called regression sum of squares, or SSR. SST stands for total variance. Because the SSE is random variation, it cannot be explained by the regression line. SSR can be explained by the regression line. The R-squared measure is the proportion of the variance of the dependent variable that can be explained by the independent variables. That is, how much variance can be explained by the regression line. This is the SSR in the example below. R-squared can then be defined as the ratio of SSR to SST. Also, because SST plus SSR, R-squared can be defined as follows. R-squared is a widely used method to evaluate the performance of linear regression. So far, we have looked at the least squares method for single variable and multiple variables. We then looked at the maximum likelihood estimates and how to evaluate the model's performance. In the next video, we will look at overfitting and regularization and implement them using SciPy's optimize function.